Hi, it's Mr. Benson here. I just want to work through, or quickly go through the electric power practice SAC. Not so much to work out all the answers, but I just want to mention some of the errors that were made here. These are things we've gone over in class a couple of times easily, and so it's kind of annoying that the same stuff keeps on happening over and over again. So, just starting at the beginning here. Now, most of you are fine when it comes to drawing the magnetic field lines around the magnet. So you do that, and that's all cool. But then you get confused with what's going on here. Now, you've got to think about what the question is saying. It's saying that at point P, the magnetic field from the magnet is equal to the Earth's magnetic field. Now, what you've got to think about is what direction that is going in at point P. Now, P is exactly in line with the end of the magnet, so the vector from the end of the magnet must be going like that. Then what you've got to think about is how these two vectors are going to add up. So you've got the vector from point P, which is like this. Now you've got the vector from the Earth's magnetic field, which is going straight up like so. Now they are going to add up so that your vector at P is going up at that sort of northeasterly direction. So that's what you need to do for that question. Now we'll scroll down a bit here. The next one caused some confusion. Now I think some of this was to do with how people were understanding the question. You will see this a little bit in some exams where the dot and the cross are indicating the direction of a current rather than a direction of the field. But the important thing here is that the current is going the same way that the field lines are going. So the cross indicates that the current is going straight into the page. The dot over here indicates that the current is coming straight out of the page. So then you've got to use your right hand grip rule. So in this case, my thumb would be pointing into the page at A, which means my field lines have to be going around like that. Most people are okay with that. Now this is the opposite. The current is coming out of the page, and so the field lines have to be coming like this. Where people made silly mistakes is then what happens at the total field here. Now what you've got to imagine is that this field at A continues, all the way to P and basically past it. So if we are going to draw the field around A at about that radius, it's coming around like this, and at P it's pretty much going straight down. Now the field from B is doing the same thing, but it's the mirror image. So at this point here, they're both coming down like that. The only logical way that they can combine is to go straight down, not up. Would the wires attract or repel each other? Explain. Now, the best answer for this, a lot of people got repel, which is correct, but they said because the field lines are going in opposite directions. Now that's not a good answer. So what you need to be doing with this one is referring to the slap rule. Now if we think again about this, these magnetic field lines from A, well, if we go and extend that out up until we're getting closer to B, so our field line from A is basically coming straight down when we're at B. So then what we need to do is to get our use our right hand slap rule in this case. Now our current is coming out of the page at B, which is where your thumb is going to go. Your field lines are going down, so your fingers need to be pointing down. Now the palm of your right hand will be pointing to the right, so that is where your force is going to be going, and so you're going to be they're going to be repelling. And you really need to refer to the rule in order to answer that properly. Okay, the force, so that's just ILB, that's pretty easy. Okay, the direction of the field produced by the loop below. This was reasonably well done, but the biggest problem with it is people seem to not know, either you couldn't do the grip rule or you didn't know which was which in terms of the current going in and the current coming out of the page. So what you've got to think about is where the current's flowing. So I've drawn that it's coming up here on the left, which means that it's going up here like that. You use your right hand with your thumb going in the direction of the current, and what you find is that your fingers are kind of curling over the loop like that. Now that's a terrible way of trying to draw it, because you can't really see what's going on, so that's why we use the dots and the crosses. And you've just got to remember that the dots are coming out of the page and the crosses are going into the page. I still have to look that one up myself, because I always get muddled up. That's why you have a cheat sheet. So dots are coming out of the page, crosses are going into the page. So there was some confusion about that. Okay, next question. Now this was frankly kind of silly, some of the things that went on with this next question, because the first thing it says is an electric motor is constructed. So we're talking about an electric motor. Now the other thing that seemed to confuse some people but shouldn't is what this is representing. It's representing a magnet here on either side of our coil. Now the coil is currently lying flat, so we're sort of looking at it on a bit of an oblique angle. So maybe my diagram wasn't perfect, but you should be able to envision what's going on here. If you think about it, the current in this case is, well, actually we're told in the first part that the current's flowing from A to B at the point we're interested in. Now that's kind of going into the page, if you want to think about it in those terms. The magnetic field we know is always going from north to south. The best way of describing that is left to right. Okay, so then we go down a bit to the direction the motor will rotate. Now lots of people got anti-clockwise, which is good because that's the right answer, but the quality of the explanations wasn't very good. Again, we're using the right hand slap rule, so I want you to refer to that. Now remember, this is a motor question, so it's not a question about flux or anything like that. You shouldn't refer to any of those generator terms when you're doing it. Okay, so right hand slap rule, you've got to explain why you're making that decision. The current is going into the page, the field is going from left to right, so according to the right hand slap rule, the force on AB will be down, so it will turn anti-clockwise. Okay, the next thing, the motor has slip rings, not a generator. So what we're talking in this case is, sorry, my washing machine's going in the background and is getting a little bit loud. So the motor has slip rings connecting to the coil of the power supply. What kind of power source must be used? It must be AC, because only AC will operate a motor with slip rings. And why? Because only AC has an alternating direction of current or something like that. You could, well, AC is alternating current. Okay, so that's one, that's one answer to that. I'm going to put some answers up on Compass. Okay, moving down. Now we've got the motor being used as a generator. So this one was done okay, although there were a few kind of silly mistakes. The main thing that I was pretty happy with is that people had the EMF equals N delta phi over delta T. Okay, that was pretty good. What is not so good is that people struggled with the fact that I gave you a frequency. Now, a frequency of 10 Hertz means that our period is 1 over 10, which is 0.1 seconds. So that is the period of the motion. But what you've got to remember here is that we're not interested in the whole period. We're interested in a quarter turn. So we're interested in a quarter of that, which is 0.1 0.025 seconds. So that is the correct time. Now if you did that, you would have got an EMF of 300 volts. Okay, so moving on to the next question, sketching the waveform of the EMF. Look, this depended on getting the right answer for the previous question, but if you were consistent, I still gave you the marks. So you should have had 300 volts or whatever your maximum voltage was. Now it's an AC signal. Now we know that because we just know that it is. This is being so annoying. So it's going to go. Sorry, I don't know why this is being so irritating. Right, let's try that again. So an AC signal, so it's going to go up and down like that, up to 300 volts, down to minus 300 volts. And what you also should be showing here is that our period is 0.1 seconds. So that's the complete sketch. Okay, what changes would have to be made to the generator to produce DC? Now, it's an AC generator. We've just been told that. Because the motor is the one that we've used previously has slip rings, so it's being used as an AC generator, and also AC is the normal product of a generator. So in order to do that, what we would need is a commutator or slip rings. But you also need to explain, and this is something that was not done well. So people would say commutator, but there is no explain part to this. So whenever a question says explain, you need an explanation. To reverse, so this is just an example of what you could say. To reverse the current when the EMF is negative, or something along those lines. Now, multiple answers for bonus marks. Multiple answers that you might talk about would be extra coils, and you might explain how that can be used to give, with the aid of a graph, you might explain how extra coils can be used to give a better output. So a diagram is the word I'm after there. Okay, so the power supply from the generator needs to be transformed. Now again, this was badly done, and there's no reason for people to be mixing up these sorts of questions when it says transformed. There is a set of equations for transformers. They are not for anything else. So if you are using something other than the transformer equations, you get nothing here. Now, the other thing is people just did sort of slightly weird stuff here. The transformer equations relate the voltage to the number of turns. So you don't need to think about anything else in a question like this. So I'm telling you what the output voltage is. The input voltage should have been your answer from the previous question. Now, as long as you were sensible with how you answered this question, I would give you full marks even if your voltage from the previous one wasn't right. You need to support your answer with a calculation. So all you needed to do with this one was just use the transformer equation in the correct form. And so you are doing, so it's just Vs over Vp equals Ns over Np. Now we know Vs and we know Vp because this is in the question. This is your previous answer. You're told one of the number of coils, so number of turns, so you've got to find the other one. The other thing with this question is that it says it's asking you to design a transformer and support your answer with a calculation. So that was maybe a little bit unclear, but it's obvious that you need to do two things. So if all you do is a calculation, you're not really answering the question that well. what I'm looking for here is a sentence or a diagram or something like that which satisfies the designer transformer part. The calculation is how you figure out what the correct number is to answer the question with. Okay, a couple of other things that were look, not that troubling but worth thinking about. I would show units on this sort of test. I know the exams just have the space for you to fill in and they don't worry about units, but if it's not there, you should be doing it. So yeah, I think I've covered the main things there, and we will go over this in class as well, but hopefully this gives you an opportunity to sort of sit down in your own time and go over some of these problems. The actual SAC will be longer. It will not be significantly more difficult, but it's pretty clear that there are a lot of slightly silly errors being made here that people need to work on.